wanted to answer that question, right? Deep learning, their understanding.
Okay, one more point. How many of you are aware? How many of you know deep learning now? Please raise your hand. With follow up with yesterday session. I just want to have a clear picture. How many of you know deep learning now? What happened? Okay, no, this actually, what the class that you are sitting, it is not a deep learning class. It's supposed to be Gen AI, generative AI class. But see, because when I reviewed, so I felt let's cover the basics. So please, if you don't know what is the inner aspect of deep learning, what we are covering now actually. What is a graph? What is leaf? What is node? What is parent and leaf relation? What is edge? So please ensure that, because the combination of this is a neuron. So this is where data structure comes in play. So now you know, so learn this step by step. Okay? Yes, you do.
Yes. All right. So yesterday's session, we deliberately took a sudden leap just to give you an actual picture of where you should have actually gotten started in 2.2 or 2.1 when you started learning machine learning or ANNs for the first time. But we realized that somewhere the depth is missing. That's precisely why we introduced a slightly tough exercise, according to you, but that is for me a beginner test case. Ideally, it should have been given in 2.2 for 2.2 students. But since we realized that you are not catching up as we want, that's the reason we started with basics first. Because generative AI deals with a lot of abstraction. Deep learning, if you don't understand, generative AI will be difficult. And if you think, with the help of ChatGPT, I will be able to do it, no. Even in your job, when you work for a company, their requirements will be specific. And whatever data sets or whatever models that you're using right now are the general ones, which are available, which are benchmarked. That is only for you to understand, get trained on ANN. But we don't want you to be the copy-paste coder. We want you to be the innovators. Because as per the requirements of your company or their requirements, you have to create a model, maybe from scratch. And the data sets will not be clean. You have to do a lot of pre-processing. And some of my students who work along with me, they said that they work in hackathons, so they know that the data they receive is not clean. So all those steps, for that you need to have this kind of depth. And that's the reason we introduced you to that notebook yesterday. And we are happy to see that you spent time, you actually took time to write on a notebook and see. That is a positive outcome for us. And today also many of my students in the PS room, they came back asking to me, this is how we tried. So actually you're trying to do that on paper. That's really good. It really helps. So you are on the right track, even if it is taking time. Don't get demotivated. Keep up the work. One day it will become easy for you. Again, we have trimmed down the exercises today. 2 basic exercises based on the code that I give you in the live session. The third exercise, we'll give it to you again. Right? The third exercise, what Srikant promised from yesterday's session will be there. If anyone was not able to solve it, do it. But there'll be one challenge exercise that I will open in the end. And if you can take some time out of your interest, complete it, we'll really appreciate that. Because we want you to understand at a neuron level what exactly is happening in a neural network. If you don't understand that, you won't understand deep learning, you won't understand generative AI. All right? So we begin with this same thing where we stopped yesterday, the notebook. So we'll discuss the solution of yesterday's assignment. And let's keep this as interactive as possible. Because most of you, by trying at home, you were able to answer those questions which you had in your mind yesterday. Right? So I have the screenshot from the notebook which we gave you yesterday. So how we will start? right? For me, how I'll start is something like this. So first I'll read what is the problem statement. It is manual backpropagation of a single neuron function. There is this diagram to just help me with the variable names, right? And then it is clearly mentioned what should be the activation function, what should be the weights, what is the data and what is the bias. So on paper, if I'm solving this, I will write W1 is equal to -2, W2 is equal to 3, X1 that is data is equal to 2, X2 is equal to 1. And where are these values coming from? It is coming from here, right? And then there is a bias here, which is B equal to 3.6. So I have all the variables clearly defined in the problem statement. So based on that, what am I supposed to do? This, sum of all Wx plus B, which is the function Z, right? I showed you in the slides earlier. Now this internal function, that is sum of all Wx plus B, is Z equal to W1 x1 plus W2 x2 plus B, right? Up to this point, is it clear? Now, there is an activation function here. And what is the activation function? It is clearly defined, it is tan H, right? It is defined as tan H here. And why are we using this? This is to introduce non-linearity, right? Now, my function Z is input to tan H function. Tan H of Z. So now where is Z coming from? From the previous step. And if I compute tan H of Z, what do I get? The final output, right? This is the final output from the neuron, which I labeled it as O. Correct? In theory, everything is right. From weights, data and bias initialization to composing these equations to applying the non-linearity, this is what we get from a single neuron. Now, you have to help me, you have to be interactive, because what you did on paper is what we are going to do now again, right? Whatever draw dot was giving you, we'll draw the same thing here and see how the gradients are flowing back. So now, we begin with the first node, the leftmost node, that is weight 1, then weight 2, then we have x1 and then we have x2. Right? Now what is the operator? Let's go one by one again. Now what is the operator here? Multiplication. So it's a star. And for W2, x2, again a multiplication. Right? Now a combination is leading to what? So there is one W1 x1. Do we have this node or no? Directly addition. Right? We have this intermediate nodes. W2 x2. And then how are these combined together? Simple addition. Right? After this, yes, W1 x1 plus W2 x2. We gave it a label like this one, right? And there is one more thing getting added here. What is that? Bias. Correct. So now these two are getting combined. How? Plus operator again. After this, what do we get? In the problem, how did you label it? N. Correct. So you arrived here. Now what is the next node? Tan H. And this is what? It's the activation function. Now this is giving me the final output O, right? So this was the complete forward propagation or the forward pass step. Up to this point you understood. Most of you got confused when the variable names were big. You shouldn't have looked at the variable names first. If you understood the concept, the variable names should not trouble you so much, because I initialized everything and gave it to you. I served it in the plate for you there, right? Now, what is the gradient of O with respect to O? this is 1, but it doesn't carry any value for the feedback process to reduce the loss function. So we have to assign the gradient of n, right? So what is the gradient of n? So again, to simplify, just look at this piece. Whenever you're getting confused, look at only this specific piece. Don't look at the other nodes. We are dealing with only this sub-problem, like how you deal with the dynamic problem or with recursion. Look at only the sub-problem. So what is the sub-problem saying? O is equal to tan h of some value, let's say z. So now, derivative of O with respect to n becomes what? Becomes 1 minus tan h square, right? So we had O equal to tan h of z, and now we are calculating the gradient. So it becomes this. So now my gradient is this function, gradient of n, or n dot grad, because we are implementing the value class, right? So this is one step which you all missed. If you calculate this, everything else can be calculated. I'll show you the smaller picture also. Remember what we said in case of addition, when you have a, b, and then you have a plus sign and a c, the gradients flow back. We do nothing. The gradients flow back as it is. There's nothing new happening there. But whereas in the case of multiplication, you have a, b, you're multiplying them, you're getting c, then the gradient gets crisscrossed, meaning now the gradient of b dot grad, is equal to a dot data into c dot grad, correct? And a dot grad is equal to b dot data into c dot grad, right? Yesterday I showed you with a simple proof of concept we did, f of x plus h minus f of x by h. So I just calculated, then I showed you along with proof that the gradients are flowing back differently in the case of plus operator, differently in the case of a multiplication operator. So you understood this. So you just had to fill this picture. You already knew derivative of tan h is 1 minus tan h square. So just fill this n dot grad. If you have this n dot grad, which is important, you can just keep computing the values here. So what will be the gradient of b? N dot grad, right? So what is the gradient of this element? w1 x1 plus w2 x2? N dot grad again, correct. Again, now we have a plus operator here, w1 x1. So what is the gradient of this? N dot grad again. w2 x2, gradient, n dot grad again. So plus operator, all good. Everything was working fine. Now comes again the tricky part, because now we are dealing with multiplication. Now what happens? What is the gradient of w1? x1 dot data into n grad, or we could say it is w1 x1 grad, right? Correct? Now again for w2, what is the gradient? x2 dot data into w2 x2 dot grad, right? Which is nothing but n dot grad. The same value, you're just assigning them different names, so that in the graph, when you're comparing the variable names and the graph, it is easy for you to compare. I would have reused n dot grad, but I wanted to build that understanding in you to make the code more readable. That's the reason I used too many variable names. So please don't tell the variable names confused us. No, I will not buy that answer. So exactly where you got confused was only at this step, according to my analysis and Shrikant sir's analysis. So whenever you're looking at a bigger problem, apply recursion in real life. Look at the sub-problem and then you solve the bigger problem. Right? Do you still have questions based on this? We are willing to spend more time. If it needs more time, we like to spend more time. But we want to know, we want that to come from you.
Yes, any questions, sir?
Feel free to ask, because if you don't understand this, the other sessions will be of no use to you.
Okay, how many of you understood? Please raise your hand clearly so that we can move forward. Okay.
Yes. So now, since this is done, you still have access to the older notebooks. So since you have access, keep practicing at home. Spend some time over weekend. Whenever you don't have this session, spend some time, change the values and see how things are playing out. That's the only way you or I can learn. There is no other magic that can be involved. So now it's time to get back to our live session. So let me unplug from this.
Yeah, as the configures one announcement here. Please change your passwords and remember them, because your friends might be using, because everyone knows his roll number, their phone number. So please change your passwords and remember them. Don't forget. Okay? Just an announcement. Just a hint.
So while I take time to set up, please open the practice notebook. We'll start exactly from where we left off yesterday. So this will happen for every session. I will remind you all only till this day. From next week onwards, whenever we have deep learning session or generative AI session, you should be ready with Tantric open. The practice notebook should always be open. So this is draw dot, this is the value class. So today, what we did manually yesterday, right, the gradient calculation, you were assigning the variable names, you did a manual calculation, then you started assigning one by one. In today's class, what we'll do is we'll write a program in the value class itself, so that the gradient calculation is automated. Every time you do a addition or a multiplication, the gradients should automatically get calculated using your value class. Right? That is what we'll try to do today. So up to this point, you have the code already, right? So this is a simple equation. We'll consider C equal to A plus B. Yesterday, instead of C, I used O. Some students got confused even there. So I'll stick to C only. C equal to A plus B is a simple thing, right? And we know from yesterday's assignment that the gradients should flow back. That is, gradient of C should get applied to A as well as B. So let's write that code.
Yeah, please listen to this carefully, because here is where the heart of a tensor starts. What is value today becomes tensor tomorrow. The same backward propagation, which he is going to now talk about, happens automatically in a tensor, which is the heart of deep learning. It's a very crucial point. Please understand how the backpropagation happens, how you configure that function. Why I am saying it is, I want you to focus on that. That's where the key is, and many people don't understand it. Tensors have it automatically. What the value class is there today, as I told you yesterday also, is tomorrow's tensor.
So first, what is required to do this propagation, back propagation? There are two steps. So from your memory and yes.
Just one. How many of you are facing login problems? Everyone is logged in? Because you
There's
want
one.
to do parallel.
There's one person here, sir, who's facing the login issue. Here.
Okay, I'll just.
Sure. Yes. So in case of a back propagation, how many steps do you think are involved? Any rough guess? At a general level, gradient calculation is definitely there. That is step 1. We'll move it to step 2. But yeah, that is one of the steps. Updation of weights? No, we haven't gotten there yet. It's only till the gradient calculation we want to do. So, in order to calculate the gradients automatically, what do you think are involved? What 2 steps are there? One, definitely it is gradient assignment. First, we need to traverse the graph, right? From right to left. And then go step by step. So, first step is the traversal of the graph. That is from right to left. What you did yesterday using draw dot. We'll write a function for that as well, because we need to automate this process somehow, right? So this right to left traversal is called as topological traversal. You can call it topological sort or topological order. So basically traversing the graph from right to left is called topological ordering of the graph. So we'll start with an empty list. And now step by step, please copy all the steps, because without this you won't be able to solve the assignment. So this list initially is empty because we did not start the graph traversal yet. And then we will have one more set just to indicate whether we visited that node while traversing or no, right? So let's say visited is equal to an empty set. And precisely we are using set because we don't want duplicates. We should visit one node in a graph only once, not more than once. So that's the reason I'm initializing this to a set. And now there has to be a method to do this, because I want to reuse this method every time. I don't want to have a small code lying around there. I want to reuse this code, and that's the reason I'm using a method. So what will this be? I'll call it build topology. Build topo, and what will this take? It will take one node as input. Now V is the node that I want to call. I'm giving it the variable name V. And what is V? V is a node from where we have to start traversing the graph. Now build topo. Now inside topological ordering, what I will check is, did I visit this node earlier or no? So if V not in visited, then I will go forward, right? If it is not a visited node, then I can do something. If it is already visited, I'm not interested in that, because by then the backpropagation already happened, the gradients got assigned. So I'm only interested in the node where the gradient calculation did not happen, so that I get to know whether it was visited or not. So if V is not in visited, then what I do is, first I mark it as visited. So visited dot add of V. Up to this point, are we on the same page? Implemented? And please don't look at the screen blindly. Type, otherwise you won't get this. Again, you look at your friend's screen, they will make a mistake, you will replicate the same mistake. This goes on and on. So type, open your laptop, type. And now, what if your node is not the leaf node? You understand leaf nodes and intermediate nodes, right? Graphs, BFS, DFS, correct? So what if your node has children? Then you have to take care of those children nodes as well. So for child in v.prev, because remember in prev, we used it in day 2 and day 3 assignments as well. We are storing the children of a node. So I'll go back to the value class again if you forgot. So in the init method, we define children, and these are getting initialized when we call add or multiplication. And you're defining self and other are the children. So that is exactly what we are reusing here, prev. So if there is a child for this node, then I have to build a topology for the same thing. So it's a recursive call now. Build topo for that child. Now for those who are not comfortable with recursion, it sounds like magic, but this is how recursion works. So take some time, add some print statements if this doesn't make sense, right? Now once you visited a node, once you built a topology for the child, now you have to add this to topo list. Because I am building a topological order, I need that order of traversal now. So that's the reason I will append it to the topo list. V, right? Now where is this V coming from? I have to make a call to build topo. So what should I pass to build topo? I want to traversal this graph. I want to traverse this graph. So I should pass C. Only one answer. What about others? We have to traverse this graph and we are doing it in the topological order. We decided it is going to be right to left. So it has to be the rightmost node. If you do it from left to right, this logic won't work. You probably have to use some other traversal. But the idea here is to go right to left. So let's stick to that. So let me rerun my cells because the runtime got disconnected once or twice. Meanwhile, you can set the build topo code. Now I will be calling build topo on my rightmost node, that is C, which is the output A plus B. And then since this build topo method is not returning anything, it is just initializing the values of topo and values of visited, I want to see what is there in the topo list. So this is it. So now what I see in my topo list are these values. So let me zoom in a little bit so that you can take a look. So it's giving me value 3, 2 and 6. But this is again in the same left to right, not right to left. So why do you think this is again left to right and not right to left? If you're good with recursion, dynamic programming, you should answer this by now. Would you like to ask now something? You guys are using LeetCode, CodeChef, HackerRank, HackerEarth. So you should answer this. This is an easy level problem, not tough. So why is it left to right and not right to left is my question. Okay. So can you explain like at node level what is happening? I'll give you the mic.
First, it will get the value of 3, the rightmost node C. Then,
can you start from the output where we gave the input? How is it going to 3? Because we started at 6 at the last node, right?
yes. So first it will go to the output C. From C, it made a recursive call to its children,
Correct.
which are B and A.
Correct.
Then once we are performing the same build topology on B and A.
Correct.
Once we perform the same topology on B and A, we'll check if there's any children for B and A.
Yes.
Since there's none, we will not be going recursive
Yes.
debug and all.
Yes.
But after that, we are appending that to the topology.
Correct.
So the first child will be first appended into the topology, then the next one. The
Yes.
same recursive call will come back, the next one. And then once the children both have been executed, the parents
Get
go
appended.
back to the parent. And then the parent will be appended to the topology.
Correct. Yes. Yes. So that was the correct answer. He explained the recursion. Now, since the depth of the graph is less, it's easy to explain and easy to understand as well. But it is the same thing which gets applied if we have W1 x1 plus W2 x2 plus B and so on, right? I think there is a operator that I missed here. So I see 6. I plan to do A plus B, not A into B. And please point out if there are any mistakes. Now we have this value. Let me run this again. Yes, so it is 2, 3 and 5 because I am doing A plus B. 2, 3 and 5. Now I am not interested in left to right. I want right to left. So what can I do? I have a tuple list. I don't want to do anything. One code change. So what gives me the right to left order? I don't want to change the logic of build topo. I want to play with the output topo. Reverse, yes. So let's do reverse and see what happens. This will not give me a list anyway, but I'll show you what is happening. Reverse, reversed, yes. So it's returning an iterator. Since an iterator, I have to use a for loop. For node in my topo list. I'm using a different cell because it's easy for me to maintain the code, right? So I'm using a different cell. You can break down your code into smaller chunks. That's the beauty of notebook, right? In IDE, we don't have that flexibility. Now let me see what is the list after reversing. It's a no-brainer. It should be reversed or the mirror image of what was there earlier. Okay, for, right, this is node. For node in topo, I got 2, 3, 5. Now I'm interested in reverse topo. And now when I print this, it is giving me right to left. This is what I want because that is how I want to solve this backpropagation. I want to mimic exactly what is happening in the backpropagation step for the assignment gradients. So I want to do exactly what PyTorch or TensorFlow does, right? Now I achieved step 1. Now what else is pending? I'll give you a few minutes. You can take some time, take a look at the code, make sure you're comfortable with this code, and then we'll proceed. So do you want me to display this code or the next cell? This code is fine?
Let them try. Let's give 5 minutes.
ఇప్పుడు ఆన్ ఉంది కదా So we completed only one of the two steps, that is traversal. Now there has to be a step where the gradients are getting calculated and assigned automatically, right? So we'll go to that step. And where do you think we have to do the code changes for that? Where? Louder please. If you have an answer, if you're guessing, that's still fine. We'll understand how we can reformat our classes so that you understand better. You're only helping yourself by giving an answer. So where do you think the assignment of gradients should happen? In the operations, correct. So inside the value class. So he gave me a correct answer. It has to happen within the operations of the value class. And please make sure that the indentation of code is correct. And that's the reason I'm using these indent highlighters also. It becomes easy for you to follow. Now we have data, we have gradient, which is initialized to 0 initially. Then prev, op, label, we understood all of these class variables. Now it is time to introduce one more variable. Now please take a close look at this, because this is not like a normal variable. It is a method variable. Now what is this? So this is to calculate gradients, right? So I am giving it a name, self dot underscore backward. And I am saying this is not a simple variable which takes int, float or string. I want this to be a method. I am in as a class variable. And for that I am saying it is a function which is lambda. If you know lambda, the inline functions, was introduced in Java 8 and then it was also used in Python. Lambda functions are quite popular. So I am just defining that it is of type lambda and this method does not return anything. So I am saying the return type is none. So understand this line properly. Spend some time on this.
Yeah, excuse me, I have a question.
Sure, sir.
What did you heard about lambda? Yes. What is that? What is lambda in programming? Very good. It is another function. Absolutely. So why we have written lambda and returning none? Why? Why? What is doing it? When do you return an anonymous function none or void? When you try to initialize the function, because you are making that function ready to be used, so that you don't get any errors. That how we initialize variables, we use functions and return none. Got it? So let us see how it is used. Please concentrate.
Yes. So again, to reiterate and emphasize on what Srikant mentioned, just like how we chose grad as one of the variables in the value class, we are defining this backward also as a method variable. And for that, we need to specify that this is a method variable. So don't treat it like any other variable. That's the reason I am providing it as a lambda function, an anonymous function, and the return type is none. Right? Now I am dealing only with the plus operator, that is addition. So in this, as your friend pointed out, we need to do some changes here in the operation, because I want to calculate the gradients and assign the gradients within the same method call, right? It makes sense to do it only here. Anywhere else you can't do it, right? This operator should be dealing with the gradients, because plus allows the gradients to flow back, whereas multiplication applies that crisscross thing, right? Inversely proportional, the proportionality changes. Whereas if you have tan h instead of subtract, in that case also you should be calculating the gradient and assigning it then and there. So that's the reason we need to have it here. That makes our life easy. Now since we decided that the name of the method is backward, and again I have one more question. Why do you think we are using a single underscore in front of backward? I can just write set.backward, right? Sorry? Encapsulation? Okay. You're almost close. Any other answers? Louder, please. Private, yes. So that is to indicate the scope of the variable. Correct. So this is of protected scope. So anyone whoever is reading my code, they know that this is a protected one. You should not mess up with this variable. So you have to use this sparingly, or if you are reinitializing them again, you shouldn't be doing that. So it is an indication. So this is a Python convention that we follow for protected methods or protected variables. Now I need to define what should happen when I call backward, right? So the definition goes here. So backward doesn't take any input because that is contained in the addition function itself. The self, other, everything, the data is coming here. So backward doesn't take anything. So what should happen? Now I am interested in assigning the gradient of self. So what should be the value that I should give as input? Other dot grad? Are you sure? Look at only this method, the add method. What all variables are we dealing with? Out.grad, yes. And for some reason, for now, I'll just do 1 into out.grad. I'll tell you why I'm using that, it will come later. But for now, I'll just do 1 into out.grad. Just to make it clear that we are taking only 1 times of out.grad, so we are taking the out.grad as it is. So that is about self.grad, which is equal to out.grad. Now what about the other.grad? What should it be equal to? Out.grad, yes. Though self.grad is same, always make sure that your code is the reflection of what should happen in theory. So don't say other.grad is self.grad. When you look back at your code, you yourself will get confused. So say it is 1 times out.grad. Now what else is pending? We assigned it. But one step is pending. What is that? Assignment is the assignment happening? So let's say I do plus here. Let me go. I will rerun my code here again. First for that I have to run the value class, shift enter. I'll run the value class here also. Now again the grad values are same, that is again because we are not picking anything. So basically the assignment did not happen at all. So what else is pending? We defined the method call, yes. The method call is not happening anywhere. So let's make the method call here. And for that, what I should do is first say that the method variable is initialized to this. Because remember we are having this self dot underscore backward, which is an anonymous method variable. But in order to call this backward, we have to initialize this. So I'm not going to call it here, but rather initialize it here. So self dot underscore backward is equal to, this is a method variable. So what should it be equal to? Underscore backward. So should I pass parenthesis or not needed? Not needed, right. So I'm just initializing the values here, right? And now I pass this completely. Shift enter, shift enter. Then I do the traversal. Then reverse. All good. So do you think the grad values are initialized now? No. Yes, they are not initialized yet. So what can we do here? While we are traversing from right to left, what else can we do? Think. Take time and think. Look at your code. Look at the notebook that you have at hand. Traversal is fine. Backward is also fine. But there is no link between these two steps. So how do we establish that link? C dot backward. But that will give me what values? Okay, the hint is something else has to be done after the last cell or in the last cell. So what is there in the last cell in my code? So I did a reverse of the topological order, then I'm going right to left, I'm printing the nodes. So what else can I do here? Think. And take a pen and paper also. Because this is a graph where you have the parent node, where you have the children nodes, and then you have leaf nodes. So edge cases are important. You should understand where a particular recursion is terminating. What is the boundary condition? I'll give you 5 more minutes. So logically we implemented how to calculate the gradients. We also did the traversal, but we did not link them together. One step is missing. You try with your code, take 5 minutes, you try, you show it to me. Show that the gradients are getting updated and then show me the graph with the updated gradients. This is a small in-class task, do it. Equal to 1.0. You initialize that. I did that in my code. If you took a closer look at the code, you would have noted that down. But anyways, I'll show you the code again. So this is my code for C equal to A plus B. I'm initializing the gradient of C. Because we know, we proved it that the gradient of any variable with respect to itself is always 1. So it is just one line of code to be added to calculate the gradients and one more line of code to generate the graphs. And the code change that I am expecting, it should happen in the last cell where you are iterating over the graph from right to left. The value class is above. We just initialized.
There is only one
Ma'am, I call the backward function
thing that we need to change.
Okay.
After when we are coming back to the parent, then I'm calling the backward function. Then the gradients are updated.
Acha, where did you make the code change?
Here in
Value class? Acha, build
build
topology.
topology, I call the backward class to zero.
Okay.
When we are coming back from a child to the parent, then we are updating its gradients.
Okay. Okay. This sounds fine. Yes. You can do that.
And then we assign the gradients to one. So before I did that, I got that.
So basically you call from here in the for loop itself.
In the for loop itself.
Okay. Okay. They are not modifying that for loop. They are modifying the for loop which is there in the topological. Huh.
This is more easy to do.
Yeah. Yes. Multiplication, they will take some time. So that is an exercise. They will catch it in exercise too. The exercise, first exercise.
Yes, go ahead. Can you just explain what you...
So before that, Niels pointed out there's a mistake in my code. I agree there's a mistake in my code. But can one of you point out what is the mistake? You can see that, right? So in that chunk of code, in backward, in under addition method, there is one mistake. Who is that? There.
Very good.
And why? Sorry? Repeat.
Now, if it is equal to C, now
Yes.
we are looking the backward function of C. Now the children equal to the children of C.
Yes.
So the backward function should be equal to C.
Correct. Yes. So he is right. So what I did was, there is a typo, there is a mistake here logically. I was assigning the backward of the child class, which is wrong. So it should be on the parent. It should be on the parent node. So that is what he pointed out. So I'll make the small change here. You also do the same changes, but the changes will not be evident because we are still dealing with one value. And we are multiplying that with 1. So this is out of backward equal to backward. This is my code. Do the same thing, and most of you are using or calling backward here. Now because I want my code to be clean and clutter free, I would prefer calling backward here. Alright. Now let me see what is happening with draw dot. When I try to implement the graph for this. Oh, it's still 0. So I missed a step somewhere. You can start with the first exercise. But this is again an netted issue. But when I'm making a function call, there is a requirement of parenthesis. So your friend pointed me out, he had been debugging the code. So this was for addition. Now we have an exercise on multiplication. So whatever you did in the addition, whatever changes you did for backward to know the topology and then calculate the gradients, similar logic, whatever is applicable for multiplication operation, you have to do that. Right? So that is exercise 1 for today.
Yes. Yeah, see,
It's on.
there are two things which is pointed out. One is how do you traverse backward, and second, that you start the gradient computation from the last node, and then in a recursive way the propagation happens again. Now, in a commercial neural network, there are about 300 or sometimes even 1000 layers which are stacked one after another. So the loss calculation or the gradient calculation which happens at the last end, at the last output, has to propagate all the way automatically back. So the tensors which you have built into those layers do exactly this. They start from the end and then start back propagating all the way to the beginning. That's how a neural network starts correcting. Okay, one is of course getting the gradients back, but apart from that there is the weight updation and all that. That is a trivial activity. See, once you know the gradient at a particular point, updating the weight is a trivial activity. You just have to use some function, some kind of optimization, and it gets happen. But what you need to understand is how the flow is happening. First you build a tree. Now this happens automatically if you are using Python. The topo is built automatically and the backpropagation happens automatically. But the algorithm they use is exactly similar to what you guys are now writing. So instead of multiplication and addition, in addition to multiplication and addition, there are all kinds of functions in between. I think at this stage, I just ask one question to what she is asking. Any function which is in the root, if you have to do backpropagation, that function has to have a quality. What is that quality? You are getting my question? See, as right now, maybe backpropagation will do through damage. It will propagate back. Similarly, in real life, there will be hundreds of activation functions through which it will go, and it will backpropagate. Now, these activation functions through which it is passing have to have one quality. What is that quality? There you go. The function has to be derivable, meaning the function should be continuous, otherwise it can't be derivable. So always you have to look at functions in activation which are derivable. If you don't have a derivable function, the backpropagation cannot happen. It cannot propagate. Forward propagation can happen no matter what you have. But the derivation which is driving, gradient which flows backward, gets blocked. Now this is important
Student
because
podcast
there are
type
certain things which we do.
student laga login అయ్యి
For example,
కొలాబ్ ఆడుతున్నారు
activation functions right now what are we seeing? Damage,
names demo student
value,
password
sigmoid,
demo
these
student
are all trivial activation functions. At a later part in this course, you will see activation functions which are statistical, which are probabilistic. Now one of the problems you face with probabilistic functions is they are not derivable. You cannot derive probability where only the mean and standard deviation of the probability is given. Then how do you proceed? What do you do? Then you do approximation. You approximate that probability with a function which is an approximation of the probabilistic distribution. And there you have to be very careful with your maths because you should not end up approximating something which is stupid. You have to be very careful with the approximation because this is not what we talked about. The gradients won't flow back. This is very crucial and you have to watch because if you have to design a network of your own, you should have implicit understanding of it.
Yes. So you should be able to see this exercise 1 of day 4. Now in this I clearly specified, we simplified the problem statement because we saw that you will need some more time to traverse more than one layer. So we are restricting ourselves to only one layer now. And what we saw in the live example was A plus B. Here in the assignment, you have to deal with multiplication operator. And for that I clearly indicated you have to do changes here. So in multiplication of the value class, you need to implement backward, you need to implement build topo. And finally, the draw dot method, when you call the draw dot method, this should be your answer. So I gave you the solution also along with visualization. So if you come down here in the code, I am giving you the boilerplate code which is not needed for you to implement. So whatever you used over the last 2 days, I am giving you the boilerplate code. Now self.backward is not initialized. You have to initialize that. Then you have to write your code here for the multiplication operation. To do the gradient assignment, you have to do the implementation code here. So your code here. And this is the initialization of C equal to A plus A into B. C equal to A into B. And whatever steps we did in the class, the same thing you have to apply here. And now I choose to do iteration this way. So be careful, I am already making a call to backward here. So you just have to implement backward and the build topo methods. That's it. Just give me a minute, I'll be back. And there is one visible test case for you to check how we are asserting your code. And in the hidden test case, we have different values. So C, A, B values change. Hard coding is going to give you only few points, not 100 points. one you dealt with multiplication operator, but here you have to do changes in the tan h. And now you don't have to worry about the code because I am giving you the solution how it should look like, and I am already giving you this boilerplate code. In that I implemented the tan h method, which is a class method. Most of you are going wrong here, and that's the reason the assertions are not passing. As a workaround, I am defining this for you already. Here in this method, in tan h method, you have to define the backward method, the class method, right? And if everything is right, then you should be able to see this graph. And what is the simple math equation we are trying to implement? It is C equal to tan h of A. That's it. The one step that scared you yesterday, we are reusing the same thing. We are just calculating the gradient. అది నేను ఏం చేస్తానంటే అది కొద్దిసేపు పెడితే తను రికార్డ్ అది వాళ్ళు ఎవరు చూస్తున్నారు సో నువ్వు ఇప్పుడు క్యారీ చేసుకో ఫ్రీ చేస్తాను This is second. Okay. Unfreeze the screen.
First exercise.
Okay. Choose it. Stop it now. Evaluate. First exercise. Evaluate. Evaluate and then stop. First exercise. Chesara. Okay. 159. Done.
Here we are going to stop the first. Please submit the second one so that we can grab it.
Exercise 1. ఇది 2 కదా 15 ఏనా
And meanwhile,
సెకండ్ ఇయర్
we will open exercise 3. You can do it.
ఏమైంది ఇంతకు అంతేనా యా ఇలాంటివి మనం ఉంటే నాకు చెప్తే నేను కూడా నెక్స్ట్ టైం హ్యాండిల్ చేసుకుంటాను
We have stopped. First exercise. We are going to pause the first second one also now. And we just remove. Please be an active participant for this demo because you're going to do this tomorrow.
స్టాప్ చేసేసి సెకండ్ ఎవాల్యుయేట్ చేసి
Okay.
ఏంటి తక్కువ ఉన్నాయి సబ్మిషన్స్ 100+ ఉంటాయి అనుకుంటా స్టార్ట్ చేసి ఉండని ఇది ఉండని డే 3 ఎక్సర్సైజ్ 1 ఓపెన్ చేసి వదులుదాం వాళ్ళు ఫ్రీ నోట్ చేసుకుంటారు డే 3 ఎక్సర్సైజ్ 1 ఇది స్టార్ట్ ఇది మనం నిన్న వాడలేదు నిన్న వాడలేదు ఇది